Okay, first we're just going to quickly describe what we actually mean by a power series. The way that I think about a power series kind of in an intuitive sense is these are basically what look like infinitely long polynomials. So in other words, every term of a power series has x to some power, x to the first, x to the second, x to the third, all the way up to x to 100, x to 1,000, x to 1,000,000, x to 1,000,000,000, x to a googolplex, and so on. And I'll just quickly start writing some examples of power series that we could see. So we're thinking about these as functions of x, even though they're written in the form of an infinite series now. So consider an infinite series from n equals 0 to infinity, where now every term of this infinite series has x dependence. For example, something like x to the power of n. And if we were to write out the first couple terms of this series, this would be like x to the 0 plus x to the first plus x to the second power plus x to the third, and so on. In fact, we could even simplify this x to the 0 just being 1, since x to any power or any number to the 0th power is just 1, plus x squared plus x cubed, and these powers will just keep going, or the terms will just keep going for this quote-unquote power series. Now, we see that in these infinitely long polynomials, or these power series, we have x's raised to powers in every single term, except what we also have is coefficients. For example, in this series, it doesn't look like it, but we're actually multiplying each term of this series by a factor of 1. So this is like 1 times x to the first, or x to the 0, 1 times x to the first, 1 times x to the second, 1 times x to the third. In other words, we can have coefficients on each of these x terms as well. So let's look at a power series with a more explicit example of that. So we can think of another example of a power series from n equals 0 to infinity. Say the power series of this time, I don't know, let's go 2 times x to the nth power all over n squared plus 1. Now in this case, we have this x to the n power. That's our x to some power term. All the other terms will be our coefficient terms. So if we start writing out the first couple terms of this series, well, when n equals 0, what this coefficient term looks like is a 2 over 0 squared plus 1 times our x term, which in this case is just x to the 0. Now when n equals 1, that coefficient term will just be a 2, this time a 1 squared plus 1 times x to the first, and that is our n equals 1 term. When n equals 2, we have plus 2 in the numerator from that coefficient function, times a 2 squared plus 1 in that denominator, times our x-dependent term, which in this case is an x to the power of 2, and we could just keep going on and on. But if we wrote out now what these coefficients look like of this power series, the first 3 terms now just look like 2 times an x to the 0, which is just 1, plus a 2 over 2, which is just a 1, times our x to the first power, plus a 2 over 2 squared plus 1, or a 2/5, times our x squared term. And we could keep adding more and more terms if we want. But again, these terms are all going towards, we're going to have an infinite amount of terms here. And the only thing I'm trying to point out in this example is we can now rewrite power series having this x to the nth term like we just saw before. But we can also have coefficients out in front of every x term. So we could write this a little more generally. For example, if we have x, or our function f of x, equaling some power series from n equals 0 to infinity of some coefficient that depends on that index n times our x-dependent n term, or x to the nth term. So these Cn terms, those are our coefficients of each power of x. And they depend on the index n. And in fact, we actually call this type of power series in this general form something kind of a jazzy little name. This is what we call a power series centered at x equals a, or x equals 0, excuse me. So this language might not make much sense now, a power series centered at x equals 0. Well, let's actually get into kind of the more generalized aspect of a power series, or more general definition. So this is a definition of what we call a power series centered at x equals a. Where a is some number. And the way we can think about this is this power series is still some function. It's an infinite series from n equals 0 to infinity. We still have our coefficient term that depends on the index n. But now we have this term, instead of just x raised to the power of n, we have x minus a, that quantity raised to the power of n. So this is what we mean by power series centered at x equals a. In the previous cases, our a was 0, so we call those power series just centered at 0. If we wrote out the first couple terms of this power series, it would look very similar to the previous. We have our C0 term when n equals 0. We have x minus a raised to the 0th power. We have our next term, which is C1 times x minus a raised to the first. We have our next term plus C2, which is that coefficient when n equals 2, times our x minus a squared term, and so on. And again, x minus a raised to the 0, that's just equal to 1. So our terms of the power series look similar, except instead of just raising x to a power, we're raising the quantity x minus a raised to some power. So let's do an example of this really quick. So if we consider the next following power series, some function f of x, being equal to n equals 0 to infinity of, let's say, 5 times the quantity x minus 3 raised to the nth power, all over 7 to the n. Well, in this case, we can note a couple things. It looks like our a, that equals 3 here. Since we're subtracting 3 from every x value before raising it to the power of n. And then the other terms outside of that are our coefficient terms, which in this case is 5 over 7 to the n. So if we were just to write out the first couple terms of this power series, well, when n equals 0, we just get 5 over 7 to the 0. We have this as x minus 3, that quantity raised to the 0. That's our first term, plus the second term when n equals 1. Well, that is 5 over 7 to the first power, times our x minus 3 raised to the first power. That's our n equals 1 term. And then finally, we can go on and keep adding more terms. So this will be 5 over 7 squared times x minus 3, that quantity squared, and we could keep adding terms forever and ever. So again, power series, we can think of them as infinitely long polynomials, where each coefficient of those polynomial-like terms depends on our index n. We call a power series centered at a when we have the quantity x minus a raised to some power of n. And these are going to be the functions or these types of infinite series that we're going to think about for a little bit going forward in class. The big questions that we have going forward are, if these are functions, well, we want to do some calculus on functions. All that rigmarole we built up in Calculus A, Calc B. We can differentiate power series. We can integrate power series. That's going to be what the next video is about. And then the big question is if these are functions, what values of x are we allowed to put into these functions? Another way to think about this is, what x values give us a convergent series? Because a convergent series, what it means in the context of power series would be, hey, we're giving our function one x value, that's our input, and in return, if that really is a function, we want one finite output value in return. So we're going to ask those questions going forward as we talk about power series. Check out those other videos.